In this talk, I'd like to discuss some S-cubed observation, which gives us some information on possible effects we would get if we injected cold plasma into an energetic particle population in the magnetosphere. I don't know how I did that. I didn't mean to, but I'll leave it up there. There are at least three situations in the magnetosphere where we have an opportunity to study these effects. The first one is in a substorm when the plasma sheet's driven in to the plasmasphere, and there's an overlap. We know that. The plasmasphere is contracted as the cold ions are stripped away. But this situation is in fact quite complicated, and I think that probably should be the last of the three we should tackle, because the effects of field-aligned currents, which we know flow along the inner edge of the plasma sheet, the effects of strong convection at the plasma sheet inner boundary and the plasma pause are likely to dominate any effects that the cold ions have on the energetic particles. Now, the second situation which gives us an opportunity is the one that Don Williams talked about this morning. That's where you have a magnetic storm, the plasma sheet is driven in, produces a symmetric ring current. Subsequently, the electric fields in the magnetosphere diminish, the plasma sheet recedes, but the symmetric ring current is left. The plasma pause is well inside the ring current initially, but then the ionosphere begins to fill into the symmetric ring current, and in fact we have an injection of cold plasma in that case. And Don Williams has looked at that, and I think the observations he reported this morning from S-cubed are consistent with the ions going out into the symmetric ring current and producing the ion cyclotron turbulence in the low beta limit, such as Dick Thorne talked this morning. Now, the third case is the one I'm going to talk about, and that's where you have a substorm and you produce a region of detached plasma in the afternoon sector, or a plasma tail, or some isolated region of cold plasma. The protons and electrons that are injected during the substorm or during the magnetic storm can have the possibility then of drifting into the detached region or isolated plasma region. It's might not be that simple, because this plasma region is going to have a drift motion as well, and so when the satellite passes through, you don't really know how long before you went through the energetic particles reached the isolated plasma region. Also on S-cubed, the apogee is only 5 1/4 Earth radii. So in fact, we've looked at about 8 or 9 months of data when the apogee of the satellite was out in the region where these isolated regions occur in the afternoon sector. We found only 4 cases, and all of these that happened were in the main phase of magnetic storms. That is, they were probably isolated regions or detached regions at other times, but they were just simply beyond the S-cubed orbit. And so it turns out that in all of these cases we had a hot plasma distribution in the ring current. The plasma sheet was drifted into the isolated region, but in all cases the beta of the plasma was at least 1. And so these calculations of ion cyclotron turbulence, the resonant energy that Don Williams was talking about, really doesn't apply, because those calculations are made for in the low beta limit. And so we have to consider possibilities such as the high beta ion cyclotron instability, or the electrostatic ones that Dick Thorne was talking about, and I'm not qualified to. But so with that as a backdrop, we have some cases where I'm going to present data from 2 of the encounters of the energetic particles with these isolated regions of cold plasma, and the results are somewhat consistent, although I want to stress that to get a real consistent picture, we have to have a lot more observations with satellites other than S-cubed that can get out and see a lot of detached regions, and not just those during main phases. Now, this first slide here shows the data we use to find the cold plasma. This is the potential between the double probe the 2 probes on the electric field experiment, and what happens here is when you're in this region here and here in a very tenuous plasma where the Debye length gets to be some significant fraction of the distance between the probes, well, then the instrument just simply saturates, and you can't measure electric fields, but you do know you're in a low density plasma. Now, the density at which this happens is not unique in that it depends on temperature, but nominally about 30 ions per cubic centimeter is where the saturation occurs. So in a typical orbit, here we go out from magnetic local time at 10 Earth radii, 10 hours, come in here at dusk, so we're going 10 hours around to dusk. We go out and we see the plasma pause here. This is the output of the search coil magnetometer, and this is the ELF plasmaspheric hiss that has been seen on OGO 5, and which always occurs inside the plasmasphere. There's a sharp saturation here at L of about 3. That's the plasma pause on this orbit. We go well out beyond L of 5, at least a 2 Earth radii separation, and we run into this very isolated region of detached plasma here. And then we come out of that, and the other plasma pause is, we're in the bulge region here, getting near it, 1600 hours, and the plasma pause and the inbound leg is much further out. We also see the plasmaspheric hiss inside the detached region. This is encouraging because this is what the UCLA group has seen with on OGO 5 cases. Also, we have another piece of consistency with a paper that was given by Kivelson and Russell at the Chapman Symposium. That is, if we look at all the cases we have, if you look at outer zone electrons across this detached region, and you look at the pitch angle distribution and the intensities, we see no effects, just as they did. So first off, the outer zone electrons don't seem to be affected. But on the other hand, this far in, even in a large storm, usually the freshly injected plasma sheet electrons are well outside the satellite orbit. So these are old electrons anyway. The protons present a different story, though. And on the next slide, I show another case here with plasma pause well in at 2.5 Earth radii, a region of detached plasma which occurred here in the orbit. In the next slide, I'll show some distributions of ring current protons or plasma sheet protons. I don't think you can distinguish the two during a storm. And here, this is the energy range, 20 keV, 30 keV, where the maximum energy density occurs in the ring current. And in this case, this is the same orbit I showed on the previous slide, and the detached region or isolated region is in the shaded band right here. And I think it's a coincidence that it happens to lie right very near this inner edge of the plasma sheet or inner edge of the ring current. This is not a consistent feature. In this case, it happened. But I've plotted here for these different energies, 78 to 138, 50 to 78 keV, down to 24 to 35 keV. The flux is at two different pitch angles, 90 degrees, the solid line, and 45 degrees, the dots. So we can look here just quickly at this plot of the proton fluxes and see that outside the detached region this way, the ratio of 90 to 45 degree fluxes is much less than it is inside the detached region. So we have a more trapped distribution in here, similar to what Don Williams presented for the main plasma pause this morning, which in this case is well inside and off this plot. But we see another feature here, and that is that the fluxes at 90 degrees actually increase inside the detached region. The next slide, I don't know if you can, I guess you can, is the same data. Here, the same pass, I've just shown a piece of it, a half-hour segment of the data. Here's the envelope of the DC electric field potential difference. This is the detached region here, the more tenuous plasma here and here. This is a color spectrogram where the red is high fluxes and the gray are the lowest, and there's a factor of 8 between the two. This is for 50 to 79 keV protons, and this is for 35 to 50 keV protons, and the horizontal axis is time, the vertical axis is pitch angle, with 90 degrees at the top, and the minimum pitch angle we sample at the bottom. This varies. For this case, it's about 23 degrees at this end of the plot and 35 at this end. This occurred because the spin axis of the satellite is roughly perpendicular to the Earth-Sun line, so that when it spins, if you're in the afternoon sector like we are here, and you're not exactly at the magnetic equator, you'll just never see a very small pitch angle. So we only get down to about 20 here. But if you just look in both of these energy channels, the color being the same all the way down implies an isotropic distribution down to the minimum pitch angle that we see. And that's what we have out here outside the detached region. As we come into it, both energies at roughly the same time developed a trap distribution with peaked at 90 degrees. And the same thing we showed on the other slide where it's red in here. It's more intense inside the detached region than it is outside. And I say this increase in the flux could have been coincidental, but if it's real, if it has to do with the detached region, then it looks like that the presence of these colines actually stabilizes this hot particle distribution to pitch angle diffusion. We know pitch angle diffusion must be going on here in this case because it was the main phase of a storm. Plasma sheet protons were being driven in, and in order to maintain anything other than a 90-degree peak distribution in that case, you have to have something to violate the first adiabatic invariant, and that's equivalent to saying you have to have pitch angle diffusion. So we can look at this, realize it's a high beta plasma. The protons are being driven inward. We have pitch angle diffusion outside the detached region, and not as much inside, or maybe not at all inside. There's another case that's consistent with this, but much more complicated. And it's not as clear that it's consistent. This is the case here. The isolated plasma region is not nearly so clear in this case. We can see the electric field instrument dropping out of saturation at quite a few times here near apogee of the satellite orbit, although the main plasma pause is again down at 2.5 Earth radii here at 6 in the morning, and out at 4 Earth radii here at 14 or 1500 in the afternoon. Now the next slide I'm going to show is just the proton fluxes across this part of the isolated plasma region. We see the ELF hiss again. I'm just going to show the fluxes across this interface, going from inside the detached region to outside. We saw the same behavior on the other side, but it's just such a diffuse region. If I showed it all, it would be too compressed. And here again, you can see the detached region here, the electric field instrument dropping out of saturation. And again, we see a pitch angle distribution peaked at 90 degrees here, with red here, high fluxes at 90 degrees. When we get well away from this region, it becomes almost completely isotropic down to the minimum pitch angle, which in this case is 15 degrees. So again, we have isotropic outside, peaked at 90 inside, and the flux is inside at least as high as outside. And in this case, again, it's about a 45-minute time period from here to here. So I say in conclusion, we have only 2 more cases to look at on S-cubed, and I guess it's a shame that we won't have more, and if they turn out to be consistent with this, or we might make some stronger claims about it. In conclusion, I'd just like to acknowledge my co-author, Joe Barfield, who I inadvertently left off of the abstract, and also all of the S-cubed experimenters who gave us their data. Thank you.
Some effects that we saw which complement this study of Jim's very beautifully. He's talking about the high beta regions. Now, in recovery phase, during this storm, when beta ranged anywhere from 0.1 to 1, we see what look like enhanced plasma density regions. And we see these because we're well outside the region of the plasma pause, going out toward apogee, and we see the flat tops go into rounded distributions. The rounded distributions only exist down to a certain energy. Using a resonant energy analysis, we can also estimate the density of these enhanced regions, and they're in the vicinity of 15 particles, 15 ions per cubic centimeter, thereabouts. And I think this lends some credence to the high beta work that Jim is doing, is that we can use this technique to be able to try to identify these regions.
I can make a further comment on that, that the recent work of Cooperman and his co-workers, and also the work of Coroniti, Fredericks, and White, would indicate that if the beta is high in the plasma, increasing the density, say in a detached region, would actually stabilize the protons rather than destabilize it. But if the beta is low, like say on the order of a tenth, increasing the density would make it unstable. So there is this trade-off.
Suppose the refilling had some oxygen coming up. Would that tend to stabilize or destabilize the protons? Is that light enough to destabilize them, or is that heavy enough to put it into a stable form?
I'm not exactly sure, but I think it doesn't make any difference to the protons. I think if you had injected, say, protons and then you asked for the stability of the oxygen ions, then it would be the other way around, that increasing the density would make it harder for the oxygen ions to become unstable. But I think adding cold oxygen would have the same effect as adding cold protons.
I was referring to Cornwall's work where he showed that putting in heavy ions like cesium would actually stabilize the ring current population. I was wondering if oxygen was that heavy.
Well, Mike Schultz is sitting right at the back of the room. I should let him answer that question anyway.
We decided that lithium was about as heavy as could be accepted in order to make the wavelength of the unstable wave smaller than the magnetosphere. So oxygen should be stabilizing.
Have enough of these detached plasma regions been detected now to sort of plot some kind of azimuthal distribution with respect to the sun? Where do you most frequently encounter them?
Well, Rick Chappell's done all that work, and he finds them in between dawn and between noon and dusk. And so that's why we look there. Maybe if we've looked other places too, and then we can confirm that that's also where we find them.